The next question I want to make sure we discuss is question number 10, because it's about concavity, which is related to, though not identical to, the skills involved in questions 8 and 9. Questions 8 and 9 only required you to use the first derivative because max, min, increasing, and decreasing are all only related to the first derivative, where concavity is related to the second derivative. Concave up and concave down is contingent on us understanding the second derivative of a function. And specifically, if I'm looking at question number 10, if I want to know where this curve is concave up, then specifically I want to know where the second derivative is positive. So just like in the previous examples, we want to talk about the line chart for y double prime, the second derivative, so that we can tell where the line chart has plus signs. That's basically how we're going to answer this question. Where would the second derivative line chart have plus signs? So let's think in the same way that we did before about how we can get a second derivative. The first thing I want to notice about y, now that I'm thinking about derivatives, is the fact that it's already an integral. So the first derivative of y is where something interesting is going to happen. When I take the derivative, and I'm using this ddx notation just to be consistent. We know we're going to use prime notation when we do the problem. But when we do the derivative of y, which I'll call y prime, is going to happen almost symbolically, because the derivative of this integral is going to cancel out, and I'm going to use the second fundamental theorem the same way I always have. The second fundamental theorem says cancel the derivative in integral. That's step 1. Step 2 is write out the original function, but leave spaces for the dummy variable. And then step 3, replace the dummy variable with x and x. And then, of course, we're supposed to multiply by the derivative of the new variable. So the derivative of x is just 1. That'd be kind of a trivial step that I'm not really going to end up showing. So it ends up that y prime is equal to x cubed plus x squared plus 1. If you're not really doing the full process anymore and you're doing this substitution in your head, that's completely okay. Do it however you want to. Now, this is the part that I have to remember. I need y double prime to analyze concavity. The fundamental theorem helped me get y prime, but I need to do another derivative to get y double prime. Fortunately, y prime is a really nice looking function now. By getting rid of the integral thing, I've actually left myself with a much easier problem to solve, because y double prime, another derivative, is simply going to be a basic derivative using the power rule. That means 3x squared plus 2x, and then the derivative of 1 is constant, so 0. Looks pretty good. Seems like I can deal with that. Now again, I need to remember y double prime is supposed to come out to be positive. So I need to figure out a line chart for y double prime so I can figure out what all of these details must look like, all the pluses and the minuses that I need for y double prime. I'm not going to bother with a line chart for y single prime because it's not asking me anything about that. If I had to do like a particle problem where I had to analyze velocity and acceleration, or if it asked me other keywords like increasing or decreasing or maximum, then I would bother with the y prime line chart. But for now, let's not bother with it because it's not asking me anything that the y prime line chart would help me with. The only thing it's asking is concave up, and double prime is the only line chart I need for that. So first thing when we make a line chart, we need to find its zeros. So I need to take my y double prime equation and I need to set it equal to 0 in order to solve. So I have 0 equals 3x squared plus 2x. Algebraically, I'll need to think for a second about the easiest way to solve that. Of course, you can use a calculator if you want to, but algebraically it does seem that the easiest way is to factor out an x in common, leaving us with 3x plus 2. And then it seems we can solve each of those factors individually. If I solve the first factor, I'll get x equals 0. And if I solve the second factor, that would be 3x plus 2 equals 0, I'll get x equals negative 2/3. So it seems that on my line chart, I'm going to have two zeros, 0 and negative 2/3. Now I don't have any boundaries on this problem. I don't have any implied boundaries or intervals to worry about. So I have negative 2/3 and 0 that I'll just kind of randomly put there. But I don't really know a good scale for the graph, so I'm not going to bother being that nitpicky. Now the next thing that we'll need to do is our pluses and our minuses. So these two critical values I can mark with zeros on my line chart. Now I need to do the pluses and the minuses, which as always involves plugging in a test point and using y double prime to test the signs of those test points. So as always, I'm just going to pick some nice, relatively easy ones to use. For example, something to the left of negative 2/3, negative 1 would be a good test point there. So in my calculator, I'll just kind of take the liberty, although you can certainly plug these things in. Negative 1 squared is 1, times 3 is 3, 2 times negative 1 should be negative 2, but again, if for security you want to just have a calculator so that you can do this without second guessing yourself, that's fine. We should end up with a positive answer though, which tells us that this section of the line chart has plus signs. The calculator may come in handy though for a test point between negative 2/3 and 0, since you're not really left with very many nice options. Most of the options that you'd have to test by hand involve fractions or decimals. So pick anything like negative 1/2 or something easy, something that you know is safely within that region though. So 3 times, let's say negative 1/2 squared plus 2 times negative 1/2. Again, notice I'm plugging into the y double prime because that's what I'm testing. I'm testing y double prime. So I need to use its equation to do these tests. So the test point gave me negatives in that section. Then I'll do one more test point. Maybe I'll pick like 1 for the last one. Now that one's pretty easy. 3 times 1 squared plus 2 times 1, that's going to be a positive answer. So I can tell where my line chart is positive, where my line chart is negative, and I can tell where my line chart has zeros. So just to conclude, and this is where the vocabulary of these things is going to come out helpful, we are now concave up anywhere that the second derivative, y prime or double prime, is positive. And it looks like according to my line chart, I have two sections where y double prime is positive. So it appears as though my answer, which I'll write over on the left just so I have a little bit of space, my answer, so y double prime, actually the way we technically phrase it is we say y is concave up. It's based on the double prime, but the function or the curve is concave up, so y is concave up on the intervals, and I'm going to write these intervals, negative infinity, because I didn't have a left endpoint, to negative 2/3 in union with 0 to infinity. That appears to be the only information that I can conclude. Now this question could have just as easily asked me about other things. For example, it could have said, where is y concave down? Well, concave down would have been from negative 2/3 to 0. Would have been where the double prime is negative. So same thing. You could have also theoretically been asked questions about inflection points. If the question had asked where this thing had inflection points, we would say that this thing has two inflection points at x equals negative 2/3 and x equals 0. Because those are the 2 points on the line chart at which the sign changes from positive to negative. In other words, the graph has changed from concave up to concave down. So all of these different words related to concavity could have just as easily been asked in this question, and we could have just as easily used the same line chart with the same process to be able to answer it. So this is an example of how you would answer if it says concave up, but feel free to have that flexibility to know that there are lots of other answers that it could have theoretically asked you for that wouldn't involve any different processes. Now, if you are familiar with the fact that a concavity or inflection point related question is a line chart question in disguise, you might want to add those words to that little graphic organizer we were making up at the top about trigger words for line charts. Additional trigger words for line charts definitely include the word concave. So concave up or down, either one could be a trigger word for line chart. And anything about inflection points, because those are theoretically additional examples of questions for which a line chart would help us think. So that's more just a review of derivative vocabulary. That's not really something related to the fundamental theorem per se, but hopefully by the time you've done a few examples on this page now, you've realized how the fundamental theorem ties in. The fundamental theorem is what helps us get these derivatives. And then we analyze these derivatives using old school techniques to be able to actually answer the questions. The last video in this series is going to walk you through question number 11, which is yet another application of the same idea.